Okay, well, hello. My name is Scott Grizzard from the University of South Florida. For some reason, um, the computer wants to, green screen my hair. Very strangely, wants to treat my hair like part of the green screen. I'm sure it'll stop when I, do something else. Probably because I don't have any light on it. Let's see if I put a little light on it. Will that fix it? Light. That made it worse, didn't it? Okay, well, we have green screen issues. Anyway, today is the 10th of September, and reminder that there is class chat in both Discord and right over there in Twitch. Twitch chat is public. The world could see it. Discord is reserved, of course, to the class, or to the two classes I'm teaching. So before we get started, there was that issue that happened yesterday at 5 p.m. So anyway, the thunderstorm wiped out the power, and I had a backup plan for the internet, and it didn't work. So I got a new backup plan yesterday. Here it is. There it is. Which way? Yep, there it is. So I got a new backup plan yesterday. So hopefully, if that happens again, I'll be able to log on with this. And obviously, I've got batteries on my laptop, so I'll be able to open up my laptop, and I've got backup batteries too. And reconnect the streaming. So if for some reason I do get knocked off in the future, I'll have a backup plan. I hoped you watched the last video for the quiz. There was only one. I did do some edits to it. I did do a little funny stuff, just because, I was disappointed that I didn't get to do a second quiz review. It was sad. So, I had some fun with the edit. Anyway, are there any questions, comments, issues, suggestions, thoughts, from the two people in chat? I assume that there's two people watching. So any comments, issues, suggestions, or thoughts? Let's see. Going forward. Okay. So if not, I'll just get started. Looks like there's no one watching. That's so disheartening. Wait, not even my TA's watching? That just hurts. Anyway, we'll get started. I'm sure that people will come in later. So last time we talked about, and we went over, let's pull up the thing. Yeah. So last time we talked, about infinity, limits at infinity. And we kind of just closed out this idea. And we did a bunch of things like the direct substitution on a poly. We'd had, the rational functions and things like that, and the fact that if they went to infinity, we could just sub in the numbers. And then we talked about what happened on the domain. But the time before, we had this idea of direct substitution, and we took a quiz with this idea of direct substitution in it. And that's really what today is. What does it mean to be able to directly substitute? Okay. And that's what continuity is all about. It's all about the limit. Now, you did this thing in you did this thing in peer leading, where you had this intuitive notion of a continuous function, right? And this idea from peer leading was the following. So let's just talk about this. So in peer leading, I don't like that color. In peer leading, last Friday, we talked about continuous function continuity was defined as draw it without lifting your pencil. And that's, a good intuitive definition and notion of continuity. So if we look at this function called the absolute value of x, okay? And this is kind of the function we just kind of want to keep in mind. It's the absolute value of x. So let's just write, it's this idea that what I have here is I have, it's goes down, it's just positive, whatever the value of x is, it's the distance away from 0. Okay. So as x, here it's positive and here it's positive. It's always positive, right? I take the absolute value of 1, I get 1. I take the absolute value of -1, I get a -1. So this is kind of the function that we just kind of want to bear in mind here. So what I want to do, let's grab this function and make a little snippet here. And we want to just kind of keep this function in mind. Now, when we keep this function in mind, let's put it up there, paste, make it a little bit smaller. We'll put it right over here. So this is just the function to keep in mind. So f of x equals the absolute value of x. Now, this function we want to keep in mind when we talk about continuity. Notice I just never lift my pencil when I draw it, and that's great. And remember that f of this function, absolute value of x, has a different definition, right? F of x equals the absolute value of x, and notice on some systems this is ABS of x, equals, and then it's got actually a piecewise definition. If I'm greater than 0, it's just x, right? If I throw in f of 1, I get 1. So if x is greater than 0, or greater than or equal to 0, f of x, right, absolute value of x, let's actually not call it f of x. Let's do ABS of x. I like that better. Little 3-letter function. Okay. So I take this little function, this little 3-letter function called ABS, the absolute value of x, and if my value is positive, if x is greater than or equal to 0, I just do that. Now, f of -1 equals 1, right? Well, 1 is actually -1. So if I'm less than 0, what I'm going to do is, and likewise, f of, or ABS, since I'm getting rid of this f, ABS of -1 is really -1. Well, ABS of 1 is just 1. And likewise, ABS of -2 is really just, it's 2, right? It's the positive version of that. But that's the same thing as -2. So if I want a formula like this, I'm going to do -x. Now, don't think of this as -x. This is really -1 times x, right? If x is less than 0, I'm going to multiply it by -1. So how do we feel about that function, 1 to 5? This is what the function actually is. And it looks like 5-pole is not working again. That's great. Well, just type your 1s to 5s into the thing, please. Okay. So it's just this idea, right? If I'm less than -1, if I'm less than 0, if x is less than 0, I'm going to multiply whatever x is by -1 to make it positive. Okay. Now this function here is continuous, right? If I don't lift my pencil, I can draw it. Or in my case, the stylus. All right. Well, let's get a more formal definition of continuity. Oh no, another formal definition, right? We had epsilons and deltas. We had other weird things. We had functions that were actually just sets. And now he's got another formal definition. Oh no. Are you ready? Are you ready for the formal definition of continuity? Let A be in the X space and let F be a function. Okay. Everybody okay with that? I've got an A, I've got an X space, I've got an F that's a function. Big definition. F is continuous at A if, for every epsilon there exists a delta. No, I'm kidding. If the limit as x goes to A of f of x equals f of A. And that's it. In other words, if the limit of the function equals the value of the function. All right. In other words, f is continuous at A if f has the direct substitution. Did I do that? Substitution. I think so. Substitution property at A. And that's all it is. If I can directly substitute onto a function, it's continuous. That's the technical definition of continuity. Wow. That's deep and short. Okay, so how do we feel about this definition? I'm continuous at a point if I can directly substitute into that point. Or I'm continuous at a point if the limit as x goes to A if f of x equals f to A. All right. So back to our example. Okay. Let's show that ABS is continuous at 1. By the way, there's this thing, the book is going to write stuff like is continuous at x equal 1. I hate that. Shouldn't it be at A equals 1? It's at 1 in the X space. But you may see this. I think that's silly, but okay. Some people find it easier to think of. So let's show that this is continuous. Well, what do I need to do? I need to show it meets the definition, okay? All right, so what I need to do is I need to show that the limit from the left equals the limit from the right equals the value of the function. So I need to show the limit as x goes to, let's do -1. -1 of abs of x equals abs of 1. So I need to show that the limit from the left equals the limit from the right equals the value of the function. Okay, so what's the limit from the left? Equals abs of -1, I'm sorry. Or it's really not going to make a difference here, right? So I need that the limit as x goes to -1 of abs of x equals, well, what is the limit? What is this function equal to by definition? If I'm around -1, what is abs of x? Okay. Well, if I'm back to our definition of abs, if I'm around -1, abs of x is less than 0, right? So it's -1 times x. Right? And that's from the definition, right? Right? Around -1 is negative. Okay. If you want that formally, choose a delta of 0.01. Either side of that, right? Anything inside of that's still negative. Okay. That then is the limit as x goes to -1, right? So -0.9 to -1.1, right? That's the neighborhood I can think of, and everything in there is negative. Well, that there is, this is a polynomial. -1 times x is a nice little polynomial. So that's going to be -1 times -1, which equals, well, 1. Now, abs of -1 equals, let's see, -1, since -1 is less than 0, which equals 1. So, limit as x goes to -1 of abs of x equals f of -1. Both of them equal 1. Thus, abs is continuous at 1. How do we feel about that 1 to 5? I just did something that was way complicated to show something way simple. Okay. Well, let's do 0. Let's let a equal 0. Okay? Let's let a equal 0 and ask the same question, okay? So what do I need to show? I need to show is ABS continuous at 0. So I need to show that the limit as x goes to 0 of ABS of x equals ABS of 0. Okay. Let's look at it. Here I've got a problem, right? Because here I'm going to have to break up the limit from the left and the limit from the right. Notice the function is different above, and I should say different left, near, and right near 0. So we need to do limits on both sides, right? I've got ABS of x equals negative 1 times x if x is less than 0, and x if x is greater than or equal to 0. So what I'm going to have to do is I'm going to have to break this up. This is now a piecewise function, and I need to, if I'm going to do this formally, I'm going to have to be careful around 0, right? So what am I going to do? I'm going to need the limit from the left. I need that the limit exists. So I need the limit from the left equals the limit from the right. Now, 0 minus. Now, I'm left near now. So I need to use the top definition here, negative 1 times x. Right? I'm on this side. Well, negative x is a nice little polynomial. And there we go. Now I have to do the right-hand side. Now, I'm on the right-hand side, so I need to use the x definition. That's now the identity. I could use ds as well. Well, 0 equals 0. And now, what is f of 0? ABS of 0 equals 0 is less than or equal to, well, 0. So the limit from the left equals the limit from the right, which is not enough, equals the value of the y value of the function. right? So, for instance, this is not continuous, right? The limit from the left equals the limit from the right. Sorry, my head's in front of it. The limit from the left equals the limit from the right, but they don't equal the value of the function. F of A is jumped up, right? So these limits might be equal, but it's not continuous at A. How do we feel about this whole process, 1 to 5? What I need to show? I need to show that the limit from the left is the limit from the right is the y value of the function. 1 to 5, how do we feel about that? Okay. All right. And this is how we prove things. I use this nice little word show, right? Show that ABS is continuous. But what we actually did was prove. Okay. We actually proved it. Okay. Oops. I'm messing up Weierstrass's name. Weierstrass's name. I don't want to do that. I don't want to mess with Weierstrass. He's important. Okay. So, one of the ideas here, if you clip over to the, if you're happy with that, that's boring. That's horrible. There's some exercises in here. On screen 2. There we go. If you go on to the notes, and by the way, I updated the notes because I found a note, a mistake. There's some exercises in here. If you want to work on it a little bit, you can actually, play with these things being continuous at various places. The things you have to be careful of are these things right here. All right. So So if you go to the notes and you go download the notes, you'll find a couple of exercises like this. And those are really good exercises. Okay, let's talk about functions that are continuous because we like these, right? Samples of functions that are continuous. There's also a definition there for continuity on closed and open intervals. Let's just do that real fast. Definition. Let D be an interval f a function. F is continuous on D if for all A in D, f of A exists, and f is continuous at A. So if for every point on the interval f of A exists and f is continuous at A, then f is continuous on the whole interval, right? If for every, I should put the for every because the for every is what's important. So if for every x value in D, that x value is f is defined on that x value, and f is continuous at that x value, then f is continuous on the entire interval. 1 to 5, how do we feel about that? Okay. All right. There's a question in chat about logs. That's not really for today, but I will be happy to answer that question. If you want to stick around later, I'll be happy to answer that question. Okay. All right. So we've talked about this. We have kind of this intuitive notion about what's going on. All right. Let's move on just a little bit. So, for example, the above here would be continuous. For example, a polynomial is continuous everywhere. Okay, so let's list some of these important functions. Okay. Polynomials are continuous everywhere. Okay. If f is, let's do this. If f of x equals p of x over q of x, if f of x is a rational function, then f is continuous. So p and q are both polynomials. P is continuous except where all right, so P and X are polynomials. P and Q are polynomials. All right. So rational functions are continuous where they are defined. Polynomials are continuous everywhere. Sine and cosine are continuous everywhere. Tangent is continuous where defined, but remember it's not defined everywhere. Okay. And those are the biggies. Absolute value is continuous, but these are the biggies. Okay. Exponential functions are continuous where defined. And so for all C, all right, and the same thing with log. So log base C is continuous. Where defined. All right, are there any questions about that? All right. Now, one of the big things about this is that I can use, so on all of these, I can do direct substitution and solve limit problems on these. Okay. All right. Any questions, comments, issues, suggestions, or thoughts? All right. How about this? This is a function. And this is going to kind of ruin this idea of continuity being don't lift your pencil. So what I want is I want to do a function that is continuous exactly 1 point. Okay? Does anyone remember our old Dirichlet function? Okay, remember that little sucker? That was an evil function, right? All right, the Dirichlet function. All right. F of x consider the following modification. So recall Dirichlet function. F of x equals, I should actually use a delta, but I'm not going to. F of x equals 0, 1 if x is rational, 0 otherwise. All right. This was this evil functions. This is continuous nowhere. But consider the following modification. What I'm going to do is I'm going to multiply this function by x. In other words, I'm going to have x if x is rational and 0 otherwise. I claim the following. G is continuous at 0. Okay? How do we feel about that, 1 to 5? Remember this function? The Dirichlet function was this horrible thing where I couldn't really draw the graph, right? It had, you know, dot, 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 and then dot, 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 right? It couldn't really be drawn. And I claim that this function is continuous at exactly 1 point. Okay? How do we feel about that? Anyone still in chat? Anyone still watching? Yeah, this one's weird. Okay. I claim that G is continuous at 0 and only 0. Okay. All right. So let's do this. Let proof. Okay. Why only at 0? Why the only point 0? That's the question, right? So what does this function look like? This function here looks like this, right? If x is irrational, it's all of these. But remember, this thing is dense, right? So it's going to look like this. For the rationals, it looks like this. Okay? And I claim that this thing is continuous at 0. So, the first part, okay? I need to show that the limit as x goes to 0 of g of x equals 0. Right? I know that g of x equals 0. Right? I plug it in there. X is rational. Right? But it's, all right. So this becomes 0 times, well, 0. And I need to show that the limit as x goes to 0 of g of x equals 0. Well, here's my graph. Right? On the irrationals, I'm here. On the rationals, I'm here. I'm going to use 2 cops on this. Okay. From earlier in the notes, right, I proved that already. I proved that the limit of this thing as x goes to 0 is 0. I already did that, right? I did that right here. So by the constant multiple law, I get negative x for that, right? So that's that. So I've shown that this is true. So that's my one condition. Now, the absolute value of x, if x is less than 0, and not if absolute value, if x is less than 0, then g of x, and g of x is rational, and x is rational, g of x equals negative x, which is less than, g of x equals x, which is less than negative x, since x is less than 0. Everyone on board with that? Less than or equal to, because it could be 0. Right? If I'm up here, basically. Okay. If x is less than 0, and that should be an and, x is irrational, then g of x equals 0, which is less than or equal to negative x, because remember, negative x is positive. Okay? If x is greater than 0, and x is rational, g of x equals x, which equals, which is less than or equal to x, which equals the absolute value of x. If x is less than 0 and x is irrational, g of x equals 0, which is less than or equal to x, which equals the absolute value of x. The lower side is the same. So by 2 cops and a drunk, limit as x goes to 0 of g of x equals 0, and g is continuous at 0. How do we feel about that? 1 to 5. A little 2 cops proof. I love that. I get 3.5s. I love 3.5s. My absolute favorite is the person who always, last semester I had someone who always said pi. I'm pi. Okay. So now to show you need the, and you need the definition of the limit to show that it's not continuous anywhere else, but it's almost the same as the Dirichlet proof, which I did in class. You just need to like have your delta be like 1/2. I'm sorry, delta needs to be like 2 epsilon, and you can show that there's no. I'm sorry, epsilon needs to be like 2 delta, and you can get away from it. Okay. All right, so now we have this idea that it's more than just don't lift your pencil, right? I can have weird things. But for the most part, we're not concerned with that. But this is a very cool kind of mind stretchy thing to get away from thinking of the limit as don't lift your pencil and think of it a little bit more formally. Okay. All right, we have one more immediate consequence of continuity, and that's called the intermediate value theorem. Okay. And the way to remember the intermediate value theorem is this. If I drop a ball, where's my ball? I think the cat threw my ball under the desk, right? Right. I think I dropped it on the floor and the cat went plack. Okay. So if I drop this pen is in front of the camera. If my pen is this high and I drop it so that it's now this high, is there a time t where the pen was this high? If I take my pen and I drop it and manage to catch it, is there a time t when it was here? Right? If I drop a ball from 5 feet to 3 feet, there's a time that it's 4 feet. That's the intermediate value theorem. It's a mathy way to say that. Okay? The intermediate value theorem says this. All right? Let D be an interval. This is all preamble. F be a function from D to R. Okay. And A and B and D. Okay, so I've got 2 points. I've got 2 x values, A and B. I've got an interval of some sort. That's my x space. All right. So here's the picture that's going on here, right? I've got X, I've got Y. I've got kind of an A that's particular. Here's an A, and here's a B. Now, if F is continuous on AB and V is some Y value between F, strictly between, by the way, F of A and F of B. All right, so I need F to be continuous. Then, so what's this saying so far picture-wise? I've got an A, I've got a B, I've got some F in between them. Here's F. Right? There's F of A. And that right there is F of B. Right? F of B is something in the Y space. F of A and F of B are in the Y space. A and B are in the X space. Now, V is some value here in the Y space between them. There's V. Okay? Now, if F is continuous on the closed interval AB, and v is some y value that is strictly between, in other words, it's not f of a and it's not f of b, but it's somewhere in between them, then there exists, okay, an x value u in the open interval AB so that f of u equals v. Actually, u would be right there. Sorry. Okay, and there's the picture. How do we feel about that? That is a very mathy way to say, if I drop the ball, if the ball goes from 5 feet to 3 feet, there was a time when it was 4 feet. How do we feel about that 1 to 5? Okay. Yeah. Okay, so let's break this down. In the x space. No, u is the time. Okay, so let's break this down. This right here is f of a. This right here is f of b. This right here is v. This right here is u. The time is u. There was a time, right? So from time 0 to time whenever it hit, right? There was a time in the middle when it was 4 feet high. So let's put our concepts. In the x space is an a b, a u. In the y space is an f of a, an f of b, and a v. Okay, so these right here are x space concepts. How do we feel about that? Okay. This is actually a very powerful thing. Well, crud. I thought I fixed this on here. Oh, I did. Okay. Okay. It actually can be. So the question in chat is, can this be another way to see continuity? In one sense, yes. I could say that f is continuous if this is true. But I'm not going to do that. I'm going to use this as the theorem. Okay. And it has a corollary called Bolonzo's theorem, which says that if f is continuous on AB and f of A and f of B have opposite signs, then it has a root in between there. So let me give you an example. Prove that example. Use the intermediate value theorem to show that x to the fourth minus x squared minus 1 has a root between x equals 0 and x equals 2. Let's do x equals 0 and x equals 2. Well, how do I do this? So, in other words, a equals 0, b equals 2, and I want to show f of x, f of u equals 0 for some u in a, b. All right. So what I want to do is I want to show a root. So f has a root if at u if f of u equals 0. This is the definition of a root. Okay. So let's see. I'm going to use the IVT to do this. So f is a polynomial, therefore f is continuous. Okay, so if f is a polynomial, f is continuous everywhere, right? Well, AB is somewhere, right? The interval 0, 2 is somewhere. So f is continuous on 0, 2. Right? If I'm continuous everywhere, then I'm continuous at this particular somewhere. All right. The next thing I need to show that V is strictly between f of A and f of B. All right. Now, in order to do that, I'm just going to plug them in. Okay, well, f of A equals what? 0 to the fourth minus 0 squared minus 1, which equals -1. F of B equals f of 2, which equals 2 to the fourth minus 2 squared minus 1. All right, so someone pull up 2 to the fourth for me. What is it? I could actually factor it and make it faster. Thank you. Now, let's see. So we've got 11. And the point is that that is greater than 0 and that this is less than 0. All right. So 0 is strictly between f of A, which equaled -1, and f of B equals 11. Okay. Thus, by IVT, there exists u in 0, 2, so that f of u equals 0. All right, how do we feel about that 1 to 5? All right, I'll do one more example. use IVT to show the square root of 2. 1 is less than square root of 2. Less than 2. Okay. So how am I going to set this up? By the way, radicals are also continuous word defined. Yes. I should put that up there, but I didn't. Okay, so let f of x equal the square root of x. Okay. A equals 1. So let's see. Yeah. So f of a equals 1, right? The square root of 1 is 1. And let's let b equal 4. So f of b equals 2. Because remember, I want these to be y-space things. Okay. All right. So what am I going to be doing next here? Well, I've already got that f of a is on one side of this thing. So what have I got here? B equals 4, so that f of b equals 2. Now, what do I need to be in between here? Is there another way to do this? Yeah, let's do a different f. I'm sorry. Let's do a different f. Now I've made it worse. Let's let f equal x squared. Let's do this. So now let's let let's let a equal 1 and b equal 2. And now we want to show that this thing is in between the other two. So the square root of 2 squared. So f of a equals 1. F of b equals 2 squared equals 4. Okay. And the square root of 2 squared, which equals 2, is in between f of a equals 1 and f of b equals 4. Thus, there is some, thus, u, there is some u so that f of u equals 2, which is the same thing as saying there is some u in 1, 2, so that u squared equals 2. And we call that number the square root. All right, so that wasn't a very good example. I've never gotten to it in class before. I've never moved this quickly, so I've never tested that example. It's a bad one. It does work. It's in the book. That's why I pulled it. And it's just a bad example. I've never gotten that far in the thing before. Okay, sorry, bad example. Are there any questions? Um, okay, so this is where we're going. I'll put bad example, lousy example. Okay, so where are we going? I should say, where are we going? Right. So next time, we'll be doing the definition of the derivative. Okay. And we will be doing and applying the definition of the derivative. All right. On Thursday, we'll do any kind of cleanup. And then because remember, the first test is next Saturday. So we'll do anything kind of left for the first test, and we will prove the product rule. The product rule, it's not product rule, the power rule. Now, the power rule itself is not on the first test, but you're going to want to see this proof before the first test. And the reason why, and I'm not saying you want to memorize it and be ready to regurgitate it, but you're going to want to see it before the first test because it helps you with one of the problems that always shows up on the test, which is one of these, like, there are a couple of options, but there are always these problems about show that, the absolute value is not differentiable at a number, or that you can, all these other things. And yes, you can do it with induction, as someone is saying, but you can also, there's a really clean way to do this with the binomial theorem that's really slick, very clean. And if you see it, it makes one of the problems on the exam, maybe two, make sense. But again, it's not itself on the exam. But it's a nice example. But that'll be Thursday. Hopefully, I'm going to finish everything up on Monday for the exam. But there might be some little thing left over. So tomorrow, of course, being Friday, is peer leading. I do have in-person office hours tomorrow. And then on campus. And then next... and then on peer leading, you'll deal with the intuition about the derivative with velocity. And then on next week's problem set, we'll deal with the derivative as a function. Are there any other questions? Okay. There's this person that had a log question for me. I'll be happy to talk to you about it, but not in this. I don't know how you are. There's supposed to be some way that you can message a person on Twitch. Please use that. Everyone else, I'll be in Discord. You can ask me questions in Discord. And I'll see everybody next week. Thank you.